On the shores of a sandy lagoon, murky water ripples fragments of soda and flotsam lap softly at the shaded shoreline. It pushes against the snouts of thirsty assembled deer. The movement is so gentle, even the most skittish of the herd scarcely notices it, but with every ripple, every tiny surge of the soupy water, a deadly predator inches closer. The crocodile is all but invisible at the water's surface, with just her eyes, nostrils, and a few scales of her back exposed to the air, looking like nothing more than waterlogged wanged. She watches unblinking as a young but wary deer steps one hoof into the water, a calculating killer poised to strike. She smells the air, sensing the thinning of the herd that will soon see her prey move out of reach, and through special receptors across her chin and snout, she detects the currents in the water that will inch her closer without having to move a muscle. She waits perfectly motionless until the time is right, and finally she leaps, exploding from the water, 20 m an hour, powered by limbs and tail of pure muscle. She lunges for the deer with gaping jaws filled with dagger-like teeth clamping down on the unfortunate leg. She immediately reverses her movement, pulling herself and her catch back into the water as the rest of the herd abandon the victim. In a stampede, the young deer struggles, straining and kicking out, but there is no use. Its limb is trapped in the predator's vice-like grip, dragging her thrashing prey into deeper waters. The crocodile switches strategy again, tucking her limbs close to her body to again spinning it, in turn spinning her body at more than one full turn per second, with the deer's limb still clamped in her jaws. As the limb is torn from the deer's body, the splashing water is stained red from shock and blood loss. The animal's struggle slows and stops, and the crocodile drags its kill underwater, leaving nothing more than a rapidly dispersing pool of blood, ripped flesh, and sinew to join the flotsam on the surface. It won't be long before the thirsty herd returns, and the crocodile or her kin will hunt once more. This ambush predator's attack is born of reflex and raw instinct, shaped and enacted by a brain that has remained virtually unchanged for an astonishing 200 million years. The way she processes her surroundings and hunts today is an echo of her reptilian ancestors of the deep prehistoric past, coordinating her body, navigating the environment, and responding to changing situations without a moment's hesitation. Indeed, not surprisingly, considering their wild evolutionary success, crocodiles are considered one of the most intelligent hunters on Earth, despite having brains that are barely larger than a walnut, far smaller than a water, making up just a fraction of a percent of their body mass. This highly efficient biological circuitry is all the reptilian predator needs to ensure its ecological dominance. And yet there is much the crocodile lacks. The reptilian brain is stripped down to its raw survivalist basics, and when this ruthless, lethal predator is compared with the humans who watch the unfolding scene from a safe distance, or even the big cats and other mammals roaming the savannah nearby, there are deficiencies in the reptile mind that a crocodile is incapable of even considering. No complex memories, no moods or emotions are to be found here, just the instinct of hundreds of millions of years of the kill. No judgments are made, no anxious searching, no contemplation, just reflexive, albeit intelligent responses to streams of incoming data, acting accordingly in ways that will further their evolutionary goal, regardless of what happened yesterday or what might be happening tomorrow. Worlds completely unknown to these most powerful of predators. In the 250 million years since crocodilians first appeared on the planet, with a similar heritage to the dinosaurs, evolution has honed the brains of these living fossils into the ultimate predatory processors, but in doing so they have missed opportunities that their mammal cousins and much later primates and humans have been able to pursue. Entire brain regions are left languishing inside the Ratian nanoscullion skull, while in mammals they have blossomed physically and metaphorically into organic computers with behaviors that are ultimately far greater than the sum of their parts. Somewhere along the way, the physical circuitry of the brain became the psychological reality of the mind. Consciousness, sentience, and sapience combined to make humans and other animals into something else, something more than just machinery. But none of this would have been possible without the building blocks that came hundreds of millions of years before. Today, the brain is the most complex, expansive, and the interdependent organ in the human body. The secret to our success, the only reason we can converse at all, seek out our culture, and build up our civilizations. But if we wish to understand how the brain came to be, we need to go back to the very beginning, far before the first mammals and even the ancestors of the crocodile, to the dawn of animal life itself. The human brain has evolved over hundreds of millions of years, built to seek patterns, make sense of complexity, and ask what is true. But even our brains can be misled, especially in an era of polarized narratives and information overload. And that's why we're excited to partner with Ground News, today's sponsor, and a tool we love using. Ground News is a one-of-a-kind website, an app that shows how news stories are being reported or ignored across the political spectrum. It lets you compare coverage from hundreds of outlets and see each one's political bias, factual reliability, and ownership, all rated by 3 independent monitoring groups. So instead of being fed one narrow perspective, you actually understand what's happening and why it's being framed a certain way. One feature we especially love is the blind spot feed. This highlights stories that are being overlooked by either the left or the left. Your algorithm might miss, just as we study the first brains to understand how life on Earth evolved. Ground News helps you think critically and better understand today's information ecosystem. If you're someone who values critical thinking, curiosity, and truth, Ground News is your perfect daily tool. So head to ground.news/hot news hot to get 40% off the Bandage plan. That's the one we use. And trust us, it's worth it. Again, that's ground.news/hot tea. You'll find the link in the description below and pinned a comment. Thanks. Now back to ancient Earth. When 25-year-old Phineas Gage was employed by the railway construction companies of New York and Vermont, New England was a place of great expansion. The year was 1848. And like many of his countrymen, Gage would play his part in the heady expansion of railroads across the northeastern United States. His peers described Gage as strong in both mind and body, bringing an iron will and persistence to anything he set his mind to. He was smart, shrewd, energetic, and well-liked, and it wasn't long before he was raised to the position of foreman. But in September of that year, Phineas was using explosive charges to clear ground for the Rutland Railroad in Vermont. He became the victim of a tragic accident while packing sand and explosives into a prepared hole with an iron rod. The gunpowder unexpectedly ignited, ripping the meter-long 3 cm thick tamping rod out of his hand and propelling it like a rocket upwards towards his face. Gage had just opened his mouth to speak, and the iron rod smashed through his upper jaw cheekbone behind his left eye and directly into his brain. The rod's full length ripped straight through the left side of the organ and smashed out through the top of his skull before continuing its journey through the air coated in blood and brain. Had landed 25 m away. Gage himself was knocked backwards onto the ground, but to the amazement of his fellow workers, he soon sat up astonishingly within minutes. Despite the gaping hole in his skull, he was walking and talking again. As he rode an ox cart back home, he took the opportunity to update his timesheets. The physician who examined him soon after said that he could see Phineas's brain pulsating through the top of his skull. And when the injured man vomited, he reported seeing a teacup full of brain matter exude and fall onto the floor. And yet throughout all of this, Phineas remained stoically optimistic, declaring that he would be back at work within a few short days. In the end, however, his convalescence was long and difficult. In the first week after the accident, he swung from optimistic and delirious and back to rational before descending into a near coma state. His friends and family readied his funeral clothes, expecting him to pass any day, but against all the odds, Phineas clung on after the doctor had cut into his damaged face to release the infection that had developed there. Gage gradually improved, and by February, barely 4 months after the accident that should have killed him, he was back working on his parents' farm, albeit with partial paralysis in his face and no vision out of his left eye. However, even as his physical capabilities returned, it became apparent that Phineas Gage was a changed man, so much so that his employers at the railroad refused to take him back, whereas before he had been driven, resourceful, and, well, like now, he was irreverent and uncooperative, stubborn and impatient, behaving in a vulgar way, and prone to outbursts of swearing. Along with a new personality that didn't sit well in social situations, he was unfocused, devising multiple plans and schemes that would soon be abandoned. His doctor described him as having a childlike manner, but with the animal strength of a full G-grown man. It was clear his body may have survived an iron rod through the brain, but apparently the man who had been Phineas Gage inside that body had not. But this isn't the end of Gage's story. Although the railroad wouldn't take him back, he was able to hold down jobs driving horse-drawn coaches in Chilal for the next 10 years. Over time, becoming more socially adapted, his personality improved, and his later employers saw no problem with his behavior. And finally, in 1860, 12 years after an iron bar tore through his skull, the man with half a brain died from an epileptic fit. What then does this remarkable story tell us about the importance and role of the brain? We, of course, consider this organ to be vital to our survival and daily functioning. It's unique in the body and having its own protective bony case, and head injuries are often feared above all others for what they might mean for our physical and mental capacities. And yet, Phineas Gage was able to continue a conversation while parts of his brain literally dropped onto the floor. Indeed, the worst of his illness was caused by infection rather than trauma. Either way, his brain had become damaged, in particular his left frontal lobe. It's this that is thought to have caused the changes to his personality while leaving him with his physical abilities intact. Indeed, our frontal lobes are now known to be where planning and organization takes place, as well as being a hub for social skills and emotional regulation. When Gage's frontal lobe was damaged, many of those functions were short-circuited, changing the way he behaved and how he came across, apparently forcing him to learn from scratch. And yet the fact that most, if not all, of Gage's original personality returned in time tells us that the brain is not a rigid computer made of squishy organic parts. It is an organ in flux which can heal and remap itself to circum the damage that is done to it. Indeed, we now know that this so-called neuroplasticity is the root of brain development, resistance, and recovery from damage. Phineas Gage is often referred to as the man who began neuroscience, and certainly his accident and subsequent recovery occurred at a pivotal time for the understanding of the brain, the central processor for the nervous system, one of the most extensive organ systems within the body, constructed from an interlinking web of nerve cells, otherwise known as neurons. These specialized cells are able to transmit a small electrical impulse across their surfaces, which can be thought of as information moving from place to place. This impulse travels at breakneck speed, typically topping 100 mph. Individual neurons can be as small as 4 microns, allowing up to 2,000 to fit across the head of a pin. Meanwhile, other neurons have long arms called axes that can stretch over 1 meter in length and have unique structures along them. that speed up the transmission of the electrical impulse. The sciatic nerve, which runs from the bottom of our spine all the way to our toes, is made of these exceptionally long cells, and yet information is passed along it within just a few milliseconds. Even the longest neurons are of little use if they're only transmitting impulses along their own lengths. Instead, of course, they must connect to other neurons, which themselves connect to others, and so on. Each neuron is capable of connecting to more than 1,000 others. Until the body is thoroughly penetrated by this organic wiring, we rely on these connections for everything that is actively controlled within the body. But where one neuron meets another, there is no physical connection. Indeed, the cell's arms reach out to one another like Michelangelo's creation of Adam, writ microscopic, coming tantalizingly close, but never touching. At these junctures called synapses, the neuron's branches come to within just 20 nanometers of each other. Despite this narrow space, a neuron's electrical impulse cannot bridge the gap. And so the cells rely on chemicals to shuttle information back and forth across a synapse. When an electrical signal arrives at a neuron branch's dead end, a flood of these so-called neurotransmitters are released into the synaptic space, which they cross in just a tenth of a millisecond. They attach to special sites on the adjacent neuron and trigger a new electrical impulse to begin. Thus, through a complex interconnected web of electrically conductive cells and minuscule chemical messengers, the nervous system calls sensing near, like those in the eyes, ears, nose, and skin, to active cells like those in muscle. But in the majority of cases, that link is circuitous, passing through a processing hub that helps to make sense of the information coming and going. And that hub is the brain. In humans, the brain, along with the spinal cord, form the central nervous system. And just as all roads lead to Rome, every single nerve impulse in the body is either heading towards or away from this central hub. Some impulses are simply relayed from sense to action, like when we reflexively and unconsciously jerk our hand away from a scolding surface, in a similar manner to our crocodilian distant cousins. For the most part, incoming information is assimilated, sorted, and responded to in a more complex way, requiring the much more complicated and interdependent network of neuronal wiring that constitutes the brain. And our human brains have grown unprecedentedly large and influential. Weighing around 1.4 G, they contain more than 80 billion neurons, making 100 trillion connections to one another and transmitting information at over 350 MF, constantly running at around 20 watts. The brain's power would be plenty to illuminate a light bulb, even in the absence of bright ideas. But all that power and complexity comes at a cost. And our big brains are expensive to run, consuming around 20% of all the oxygen we breathe and the energy we produce. However, this is not the case for every animal. Some, like spiders, allocate up to 80% of their bodies to their brains. Others, like koalas, don't even fill their skulls. Squid, cuttlefish, octopuses have a donut-shaped brain that surrounds their food pipe, meaning that if they eat a meal too large, they can give themselves brain damage. But this isn't as much of a disadvantage as it might sound, because these animals have a far more distributed control of their bodies, music, with a greater number of neurons in their tentacles than in the brain itself. In this way, while the central brain can exert a sort of top-down control, each of their tentacles can act independently. Even the human brain is subdivided to an extent, as the fateful tale of Phineas Gage reveals. Not every part of the brain is necessary for every function. There is the smooth, dense cerebellum that plots our movements, the limbic system that stores our memories and is the seat of our judgment, and the lode cortex from which most of our thoughts and learnings originate. However, just like our fingerprints, the finite anatomy of every brain is unique to its owner, and somewhere within that tangled web of neurons and neurotransmitters, amid the chemical and electrical toing and throwing of a constant stream of information, something truly remarkable has emerged in humans and in many other animals, the spark of consciousness, transforming a mere brain into a mind. Most simply defined as a subjective experience, consciousness is the idea that to be a human or a crocodile or an octopus feels like something. Music, that information isn't merely relayed through the brain, but it's considered, and we somehow become aware of it, although we might not always have the words to describe it. And a crocodile or octopus, certainly can't we have an awareness and responsiveness to the world that lets us experience what it's like to be human, crocodile, or octopus. And each species, indeed each individual's experience, is entirely unique. From consciousness comes sentience, the ability to experience distinct feelings and sensations, as well as the positive and negative emotions that those sensations can invoke. Indeed, sentience within the animal kingdom is a strongly debated topic. It's obviously difficult to measure and interpret in creatures who don't share our communication systems. Instead, scientists carefully observe behavior and consider the evolutionary origins of each animal. As a result, most consider the vertebrate animals, including all mammals, reptiles, amphibians, birds, and fish, to be sentient, as well as a number of invertebrates, including the octopus and its cephalopod relatives, along with lobsters and crabs. And finally, layered on top of sentience comes sapiens, or wisdom, which is the ability to think, to learn, and to apply considered concepts to our behavior, especially in novel environments. Those who can think about thinking have achieved this lofty abstraction. Once thought to be the sole domain of humanity, most scientists now agree that whales and dolphins, along with chimpanzees and possibly octopuses, possess this most advanced this quality. And so it would be easy to assume that a larger brain equates to a more developed one, and one with greater abilities like emotional sentience and sapience. And while big brains may come with more neurons capable of making more connections and theoretically more advanced processing, the widely varying structure and function of different animal brains means that the correlation is not always a straightforward one. Indeed, crocodiles are some of the most intelligent hunters with a brain that is the size of a walnut, while shrews dedicate a tenth of their body weight to their brains, and no one is arguing for their intellectual supremacy. But if brains are also different in size, form, and function both among animal species and within them, then how can we hope to find a common theme? How can we hope to trace them all back to the first brain if every animal uses their organic processor in a different way? How can we know how the first brain was used? Scientists have long pondered this enigma, and they've discovered a great deal in recent years. 14 million years ago, an ape balances on the branch of a spreading fruit tree. Some 10 m off the ground, she secures her position with claws that dig into the smooth bark as her muscles twitch and correct her movement almost constantly. That leaves her front paws, her hands free to methodically strip the twigs within her reach. Her light digits, her fingers make short work of the protective spines and waxy leaves, tearing them away to get at the clusters of small fruits nestled within. But while her fingers work, her attention is elsewhere, large eyes darting among the swaying branches around her ears, twitching for the sounds of hoots or bellows that might give her advance warning of approaching threat. She is smart, among the smartest of all the primates on the continent, and the baby in her belly will be the ancestor of the entire human species. And yet the brain of this ancestral matriarch betrays nothing of the revolutions to come inside her skull. The computer that drives her thoughts and behavior is similar in size and complexity to those of gorillas, chimps, and orangutans today. It will take more than 10 million years for that to change. Some have suggested that it was the permanent move to walking on two legs that necessitated our ancestors to grow larger brains. But while the first truly bipedal apes appeared between 4 and 6 million years ago, by all accounts, the brains of these animals, these ancestors, were still small, two-limb walking, freed up limbs for carrying food and offspring in an ever-changing landscape of dense forest, broken woodland, and savanna. Indeed, there's little doubt that bipedalism was an innovation that allowed human ancestors to stride through a changing world, but changing stances wasn't actually that much of a computational challenge. And so it wasn't until around 2.5 million years ago that the brains of human apes began to grow larger, continuing changes in the environment forcing them to begin to create and use tools. They would be simple at first, but an obsession that will lead to all the art on planet Earth and to the device you use to watch this today. Those individuals who were born with brains that were marginally larger and more complex than their peers had better dexterity with those tools, allowing them to survive, reproduce, and pass on their large brain genes. Alternatively, rather than the physical instruments of survival driving brain growth, others have suggested the catalyst to be the intangible development of culture. Those born with slightly larger and more complex brains may have had better memories, emotional sensitivity, and quick learning capabilities. And again, those whose brains allowed them to keep up with the rapid increase in communal knowledge and the intricacies of its application were more likely to survive and thrive. These are all good reasons why big brains were favored in the ancestral human line, but the question remains as to why it only happened in this line and not on the branches of the tree of life that would lead to the other great apes. The initial answer may not lie in the environmental changes or the physical and cultural innovations, nor even within the brains themselves, but in our ancestors' muscles. All vertebrates, the bite muscles, are responsible for closing the jaw and are the strongest muscles in the face, completely enclosing the skull. They are so strong that they actually reinforce the bony carapace of the skull, holding it together firmly. However, studies into the genes that control these muscles' development reveal that they were weakened by a chance mutation around 2.5 million years ago. Researchers believe that the looser muscles wouldn't have constrained the skull's expansion as much as their unmutated counterparts, allowing brains to grow larger with less resistance. After that, human brain growth seems to have snowballed thanks to positive feedback between biology and behavior. Larger brains needed more fuel, but they also created opportunities for those who bore them around 2 million years ago. Larger brains allowed early humans to develop tools that they could use to kill and butcher larger animals, giving them easier access to meat than ever before. Since meat is a richer source of nutrients in fruits and grains, this richer diet could have helped to fuel even more brain growth and even more hunting prowess. It's also likely that as Prometheus gifted the spark to humanity in the Greek myths, the taming of fire played a pivotal role, perhaps begun by chance, and yet soon key to our species' very way of life, with cooked food being more easily digested and providing more nutrients. This meant early humans could scale back on the amount of digestive tissue they needed and invest those resources into the brain instead. In this way alone, among the great apes, and at a faster rate than ever seen before, the modern human brain came into existence some 200,000 years ago, piloting us into the realms of technology and civilization ever since in a way that our distant ancestors would scarcely be able to comprehend. And yet heading back to hundreds of millions of years before the last common ancestor of all life on Earth did at least have a kind of brain to begin with. Just like we may struggle to conceive how life itself, born of other life for generation after generation, could be born from non-life in the beginning, we may also grapple with how something as complex as a brain could arise for the first time, but its origins are in fact much deeper than we might imagine. As far back as 3 billion years ago, or even earlier in the Archean, the first bacteria in Earth's oceans would not have gone very far if they hadn't been sensitive to the environment around them. Their metabolisms relied on absorbed nutrients, including gases like carbon dioxide and metals like iron and manganese. It's very likely that these first bacteria simply happened upon nutrient-rich pools by chance, surviving while their kin who found themselves in a molecular desert simply died. But there was a lot to be gained for these simple single-celled organisms when they learned to sense and respond to changes in their surroundings. As single-celled organisms became more advanced, the scope of their chemical sensing followed suit. Photosynthesizers like the cyanobacteria that built stromatolites may have learned to sense sunlight, enabling them to move upwards through blanketing sediments and stay within its warm embrace. And eukaryotic cells with their more complex internal and external workings became sensitive to myriad chemicals at once, including ones that they themselves made. Indeed, eventually it was the sensing of its kin that would help single-celled organisms assemble themselves into multicellular organisms. For the first time too, the closest single-celled relatives to animals are the quantovligulates feeding on bacteria. Most spend their lives free-floating as individual cells, but some species can also form colonies with individuals living shoulder to shoulder in balls or grapple-like clusters. The quantovligulates developed a new way of communicating between individuals using electricity. This electrical signaling and sensing is similar in many ways to the passage of electrical impulses through our own neurons. Indeed, there's every reason to believe that the quantovligulates invention, or something very much like it, was the foundation on which our nervous systems began. Thus, during the distant transition to multicellularity in those near unfathomably prehistoric seas, the ability to sense and respond to the external environment was co-opted some billion years ago or more to help these larger and more complex organisms sense and respond to changes within their own bodies. This chemical and electrical signaling that had been around for at least 1 billion years ultimately formed the basis for the earliest nervous systems. In the beginning, though, it would have been far from organized, and those organisms who could make sense of the electrochemical storm inside themselves would be the ones to survive. Chemical signaling is slow, but electrical signaling has the potential to be much faster and more direct, and so gradually order was achieved, the first electrical neurons and chemical synapses taking shape within early animals' bodies. But what role did these nervous systems play? Why were they needed in the first place? Well, today there are two schools of thought. The first is that these internal signaling systems evolved to do what they had always done, what they apparently continue to do even in our own bodies, to sense and react. This so-called sensorometer view says that nervous systems evolve to link with what is sensed to the action in response to it. We can see this simply when we pull away from something sharp or blink in answer to a bright light in our eyes. We may not be aware of it, but sensory motor reflexes are core to our autonomic nervous systems, which detect changes in our internal conditions like temperature or dissolve carbon dioxide and take action among the various organ systems to keep things working as they should, with such obvious samples in our own bodies and striking precedent from the single-celled creatures that came before. It may seem like this is the only possible explanation, but the alternative view takes into consideration just how different we are from our distant single-celled ancestors. It acknowledges that when you're wielding a body made of many, many cells, responding to a stimulus is no trivial matter and needs to be coordinated. If it's to succeed, each muscle needs to be activated in the correct sequence, while its counterpart for performing the opposite action needs to relax, or else we'd end up splintering our own bones. Even considering the action of a single muscle involves signaling to thousands of individual muscle fibers. If any of those failed to get the message, then the muscle would be torn from the inside out. And so just as it was muscles that allowed the expansion of the human brain some 2 million years ago, it was the invention of muscles in the first place that set the evolution of nervous systems and ultimately the animal brain itself into motion. With an electrochemical nervous system in place, it's not hard to see how the earliest rudimentary brains came about. Concentrating more neurons in a single place, usually close to the sensing organs, would allow for feedback loops in the electrical signaling, creating the kind of logical dependencies and responses you might find in a computer circuit. Information can then be processed rather than being merely relayed, as the circuits determine whether a piece of information is significant enough to be acted upon. Music, building upon these logic networks, just as computers do with an increasing amount of physical neuronal hardware, the knots of nerves became hubs, and it's likely that both sensory motor and action shaping coordination were forces driving the evolution of the first nervous system and brains, and may even have played separate but adjacent roles in the same organism. Though no fossils remain due to its hypothetical fleshy form, scientists imagine a primitive free-floating jellyfish-like organism. It may have developed an action-shaping brain to coordinate movements around its mouth to help food to move in efficiently, but it may also have developed a second neuron hub near the top of its dome, capable of sensing light levels and triggering the release of a daily cycle of hormones to keep its internal machinery working. And over time, those two hubs may have migrated or grown together to create a single brain capable of exchanging information about the entire body and the external environment. Once a precedent had been set for brain-like circuitry, the standard rules of evolution took hold to favor the development of larger and more complex brains in animals that would benefit from larger and more complex bodies. Those who followed a conservative evolutionary path, evolving towards a simple life of seafloor grazing or mindless floating, could make do with the bare minimum of coordination and response. But any animal that attempted to grow large, move fast, or adopt new ecological roles needed cognitive circuitry that could cope with the challenges those niches posed. And in the end, this proved to be the aeropods with the need to coordinate their jointed legs, the chordates, including all fish, mammals, reptiles, amphibians, and birds, and a single group of mollusks that grew arms, the cephalops. Although later on among each of these groups, scientists have seen that it's not just the physicality of an animal's body that drives brain development, but also the challenges of social organization. Animals that live socially also need to consider the behavior of others in their neuronal logic, adding an extra level of complexity to the mental work they must do. However, in general, having a brain, even one that has been boosted by the demands of social living, doesn't necessarily equate to having a mind or a subjective experience of the self. Indeed, the earliest brains were still most likely fully autonomous. Like unconscious awareness, feeling, and sentience would come later. That most fundamental aspect of the human condition, initially emerging as unintentional properties of the organic wiring within the brain. In a moration of starings, each bird follows a simple set of rules to stay aloft, to stay alongside, but to avoid its neighbors. Viewed from a distance, the entire flock creates dynamic shifting shapes that startle in their beauty and complexity. It's hard to pinpoint the scale at which flight turns to art, just as it is hard to pinpoint the precise origins of consciousness. Some researchers think the awareness of the self is a relatively late development, that you need to be able to hold multiple inputs, memories, and conditions together to be able to experience their results. An alternative perspective suggests that the fragments of consciousness can be assembled gradually. Sensation, indeed, this means the first to appear may be the base primordial feelings like pain and thirst. By studying how animals respond to an injury, scientists do their best to establish whether they are experiencing pain as a conscious feeling, whereas crabs and shrimp groom and fuss over damaged legs. Their insect cousins never seem to notice entire missing limbs. On this basis, the former group are considered sentient, while insects are not. There is, of course, an evolutionary advantage to feeling these primal emotions, awareness of them allowing more than just reflective responses. This means that animals can remember and avoid things that cause them pain or act preemptively in the future to avoid thirst. And so over evolutionary time, these isolated intrusive feelings become more coherent, and others may join to build a more complex mind alongside the complexifying brain that can support it. And so from its origins in the sensory systems of archaea bacteria through the coordination of multicellular creatures and the unique demands of social survival, the brain has become an essential part of animal existence. But have brains and animals always gone hand in hand, and which truly came first? The warmth of the sun kisses your skin as you drift from sleep to waking. You easily stretch into its embrace, feeling the gentle flow of water against your arms, opening one eye and then the other. You're momentarily blinded by the early morning glare spearing down into the cave. But it's not long before your vision adjusts and the world before you resolves into glittering Christmas. All is as it was before you slept. And as you shake the last of the night's grogginess from your limbs, you waste no time in clambering from the comfort of your den. Striking out in search of food, you traverse your usual route across the rocky field, turning over small rocks, probing the crannies for shrimp or snails, anything that can sate the nagging hunger that the morning always brings. When suddenly the sun is eclipsed and a strange smell tugs at your senses, you whip around to catch a glimpse of the intruder and linger on the lawn, enough to make out a vast shape floating not 3 arms lengths away. It's huge, many times your size, with skin that is black and smooth. The sunlight glints menacing wide flat eyes, as well as the curving shell on its back, and its 4 limbs jerk and fold rigidly in horrifying symmetry as a cloud of bubbles bursts forth from its mouth. You are already turning to flee. Your body responds to the terror vibe without trouble. In your conscious mind, your skin shifts now to a textured gray, blending in with the rocks and sand of your hunting field. You're already moving your 8 arms, taking turns to push and pull you away from the floating horror as you release your ink along with a pulse of water through your siphon quadrant. Jet away, keeping one eye on the unthread, all thoughts of your empty belly forgotten. But for all its size and strangeness, the alien creature is slow, or at least it doesn't seem inclined to attack. Having reached the safety of your den, your skin is now black so you can melt into the shadows, but your eyes are still open, and you watch as this thing awkwardly bends and folds its ungainly limbs to clumsily navigate the reef. The bubbles continue to rise, but they don't seem to offer protection or speed. You begin to think that this creature is as harmless as the basking sharks that sometimes visit, so you creep over to the entrance of the caves of the Kaluk. You watch it poking about the reef, and as awkward as it does still move with purpose, climbing across the rocky field with a kind of methodical drive that reminds you of yourself. Music. There is something behind those flat, glassy eyes, something very much like a mind. The next time it passes close, you stretch out one sucker tentacle to greet it. Octopuses and humans, like the ones in this interaction, both sit in the upper branches of the tree of life. They are granted this lofty position, not because they are the pinnacle of evolution. Indeed, in a process that is always ongoing, there is no such thing, but because they just happen to be alive right now. Contrary to what the early philosophers of science imagined, evolutionary change doesn't look like a ladder beginning with a primitive organism, which then transforms stepwise into an ever more advanced one. Rather, the changes that are wrought over millennia create new organisms that can adapt to their unique environments while the original lineage also continues to exist and transform. This way evolution does create incremental change, but much more significant are the splits that build a densely branching tree of life. Each branching point represents the moment that two creatures diverge the last common ancestor. And the deeper the branches, the more fundamental the differences between animal groups, and in theory, the more separated they will be at the top of the tree. This means that if we look around our fellow animals at the top of the current tree of life, our closest neighbors will be the ones to whom we are most closely related. The great apes and other primates together, we sit within a sea of mammals, and in the distance we might see birds, relatives, fish, and amphibians. The octopuses, by comparison, are far more distant, accompanied by squid and cuttlefish, almost lost among a crowd of their fellow invertebrates. They are so distant that when we trace their branches back through time using genetic evidence, they do not connect to our own for some 750 million years. They have been diverging from us for almost as long as animals themselves have been around, and yet despite their differences, their distance from us at the top of the tree, and their deep evolutionary separation, both human and octopus seem to share something unexpected: the spark of sentience inside their brains, inside their minds. Humans are among a select group of mammals that have large and complex brains in which show levels of consciousness and sentience that these organs seemingly allow. But octopuses also behave in ways that make scientists believe they are sentient and intelligent. Along with cuttlefish and squid, these cephalopods are clearly elevated above the other mollusks in their kin in terms of what they can do and how they react to the world around them. Given the depth of octopuses and humans' evolutionary separation and the myriad organisms along each of their branches that don't share this particular spark, it's clear that large and complex brains must have evolved independently along both of these branches. And considering the last common ancestor of these organisms existed at such a pivotal time for all animal evolution, it's natural to wonder what the brains of this common ancestor looked like and exactly when the seeds of sentience were sown. There are several ways that we can try and pinpoint the origin of a specific organ, like the brain molecular clocks make use of the universal language of genes and proteins that help to build every piece of organic machinery on Earth. Scientists realize that proteins mutate at a constant rate throughout geological time and have used these calibrated clocks to estimate when the genes that code them came into existence. Using these methods, the genetic origin of the nervous system has been pinned as far back as 700 million years ago, during the Cretaceous period, when the Creator planet was gripped by a seemingly inescapable ice age lasting some 100 million years. Unfortunately, both the inhospitable conditions on Earth at the time and the likely soft-bodied and microscopic nature of life at the time make the existence of any physical evidence from the period unlikely. Not only that, but there are plenty of assumptions about molecular clocks, which may or may not hold true over such a vast gulf of time. Do the proteins and genes mutate at a constant rate, and are the brain coding genes even the same as they always have been? It's clear that more evidence is needed, and so an alternative approach is the more traditional one used by paleontologists in tracing the organ itself back through the fossil record. This method has been used with great success to track the evolution of vertebrate skeletons, mollusk shells, and plant structure. But despite the nervous system's importance to animals, its strictly cellular nature has offered little in the way of fossil record, even in relatively recent times. Indeed, the unmineralized soft tissue is one of the first things to decay upon an organism's death, making its long-term preservation vanishingly unlikely. But there are still clues to be found in the parts that do end up being fossilized. Most of what we know about brain evolution among ancient humans, as well as all vertebrates, comes from endocasts. These three-dimensional molds are created by sediments that get inside the enclosing carapace of a skull long after the brain tissue has rotted away. Sometimes paleontologists they make the endocasts themselves, filling a fossil skull with plaster to create an impression of the space inside. And once in a while, these endocasts can contain something more. In 2004, an animal fossil collector found a strangely shaped lump of rock on a beach in southeast England, which turned out to be the brain-like endocast of a 130-million-year-old relative of the dinosaur Iguanodon. But the outer surface of this lump also retained details not commonly seen in sedimentary brain molds. On closer inspection, this cast contained blood vessels and capillaries thinner than a human hair, as well as some textures of cortex tissue. Membrane ripples in that membrane were reminiscent of the folds that may have been present on the surface of the dinosaur brain. But unfortunately, the pickling process of the Cretaceous swamp was unable to preserve the neurons themselves. Despite this, it is clear that endocasts can be surprisingly enlightening. Studying them among animals that are closely and distantly related to one another allows paleontologists to track the development of brain regions across disparate groups of them through geological time. The 130-million-year-old Iguanodon brain endocast appears to have an overall structure that is similar to the brains of modern-day crocodiles and reptiles, and although intelligence is only loosely related to brain size, scientists estimate that the ancient animal was at least as smart as a modern crocodile. But there is also much that the endocast can't tell us. The complete absence of internal brain anatomy means that it's impossible to identify structures like the hippocampus and basal ganglia in humans, and of course, skull endocasts can only be formed for animals that had a skull in the first place. This method can tell us nothing about brain evolution in the other 95% of animal life. However, Though the fossil preservation of delicate organic tissues is extremely unlikely, it isn't impossible. Sometimes sedimentary conditions conspire to inhume purely organic tissues before Dessau's measure. Sediments of the Cambrian period some 500 million years ago, this fortuitous preservation happened surprisingly regularly. Animals died and fell into dense clays on the seafloor where their bodies were trapped, compressed, and isolated before much decay could take place. Their body tissues were then replaced by a kind of rigid carbon plus phosphate and clay minerals, preserving organic details with remarkable clarity. With this process occurring throughout the deceased animal, organic rich films in these exceptionally preserved flattened fossils give paleontologists an unprecedented window into the nervous system. On Earth, one such animal is Stanleycaris, a radiodont that is related to the fearsome predator Anomalcaris, to whom we dedicated an entire documentary. But Stanleycaris rarely grew longer than 20 cm. The animal had 3 eyes, 2 raised upon stalks, and another large central eye in the center bulge of its head. And in at least 84 specimens recovered from the 56-million-year-old Burgess Shale of Canada, scientists are able to see the brain behind those eyes as well. These flattened fills show a dense accumulation of carbonary tissue inside the animal's heads. The brains are formed of 2 segments connecting the eyes and the front claw, and researchers believe that they can trace the visual processing center that links the eyes as well as the nerves heading into the flexible grasping appendages. Another relative of the predatory animal is a gilled lopod called Kridma, known from rocks in northern Greenland that are between 530 and 515 million years old. And in this animal, 2 seists have found carbon impressions of a diminutive brain that connects the eyes and the frontal appendages. In this older specimen, however, there seems to be only one central section to the primitive, even pre-reptilian brain. A recent discovery from China, however, casts an even more illuminating light on the evolution and role of early nervous systems. Cardiodactylon is an armored lopod, a member of an extinct group of soft-bodied invertebrates that are most closely related to the velvet worms of the southern hemisphere. In 2022, paleontologists reported finding an intact specimen among the 525-million-year-old Chengjiang fauna in China. The flattened fossil is just 1.5 cm long, but is preserved in exquisite detail, showing a segmented body and a separate head, as well as the exceptionally preserved knots of nerves that run through both of these structures. But it was the structure of the nervous system, however, that got scientists most excited. Throughout the length of the body, the nerves appear segmented, feeding lad-like into each pair of the animal's legs. But the concentration of nerves in the head, the brain, appears very different, isn't segmented in the same way, leading the researchers to conclude that it originated separately from the body network. This in turn lends support to some of the theoretical ideas for the role of early nervous systems. It's conceivable that the segmented network of nerves throughout the body evolved to help coordinate a novel abundance of legs performing an action-shaping role. Meanwhile, a separate knot of nerves formed inside the head for processing and responding to incoming sensations, performing a sensory motor role, and probably also exerting a kind of top-down control like the brain of a modern-day octopus. And so it turns out 500 million-year-old carbon films tell us much more than we can reasonably hope for from such ancient long dad creatures, but they can only go so far. The brains and nervous systems that they preserve are already established enough to show up in the fossil record. They were early primitive even, but were they the first? Surely there must be some even more simplistic knotted nervous network that represents the very first foray into electrochemical control, but where might we find them? Comparative anatomy can point us in the right direction, using modern-day descendants of each animal group to tell us when the major changes took place. Sponges are considered the most primitive of all the animals, branching onto the bovine sometime between 800 and 700 million years ago, and modern sponges have no nervous system or brain to speak of. The next came the Cnidarians about 740 million years ago, whose living descendants include corals and jellyfish. These animals have a network-like nervous system, but no brain that we would recognize. But after that, the branching of the animal tree becomes complicated. So much happens in such a short period of time at the beginning of the Cambrian period, with the vast majority of animal body plans springing into existence in the blink of a geological eye. Indeed, we produced an entire documentary on this incredible era that you can watch after this one if you missed it. Animals like worms, aeropons, muscutinoderms, and chordates all burst onto the scene at once, and all of their modern descendants have a brain. It seems unlikely then the major revolutions will lie somewhere along the tangled knot of innovation that marked the end of the Proterozoic and the beginning of the Phanerozoic some 550 or 600 million years ago. The Ediacaran period was in some ways a warm-up for the Cambrian explosion, but for the most part, the organisms of the Ediacaran appeared to live quiet, isolated lives. A lack of track marks across or through the seafloor suggests that they didn't move around much, and even when many creatures are found closely clustered together, there's little evidence that they interacted with one another. Indeed, on the vast majority of fossils that have been found, there appear to be no sensing organs like eyes or sensitive probing tentacles. With little movement and little external input, these organisms wouldn't have had much use for an expensive processing center, and yet genetic evidence suggests that the foundations of nervous systems had already been laid down in had their molecular underpinnings in place for 100 million years by the time many of the Idirans were gracing the seas, may be that these organisms were simply developing their nervous systems quietly in the background, and that this slow burn was a necessary part of building a successful multicellular body. Indeed, even relatively mundane life processes like digestion, circulation, and excretion needed to be coordinated in entirely new ways when that life grew bigger. And it seems likely that internal electrochemical signaling would have had to have evolved in response, even if it ended up leaving no trace in the fossil record. And of course, there are some exceptions to the rule of placid isolation among Idiocarans. Some organisms like the mollusk like Kimbrella and the worm-like Sprena have a certain symmetry about their bodies that suggests that they have a head, as well as being associated with trace fossils that may be signs of their movement through the seafloor sediments. Music, if they crawled, slithered, or moved with intention in any way, then they must have had a nervous system of sorts acting in action shaping mode to coordinate that movement, and/or in sensory motor to direct that movement towards food and safety and away from threats. The interpretation of these fossils, however, as well as their purported behavior and their possible animal affinities, is still in its infancy right now. There's just too little evidence to say whether these animals really did move and respond to the world around them. But then at the beginning of the Cambrian period, everything changed. And over the following 10 million years or so, the seas were teeming with an entirely different kind of life. The Cambrian explosion was not just a radiation of new body shapes, but also a sudden expansion of ecological relationships, and roles animals expanded into new territories, no longer limited to the two-dimensional world of the seafloor, but roaming down into the soft sediments and swimming up into the open water. And with this new three-dimensional territory came new opportunities for food filter feeders, active grazers, burrowing browsers, and apex predators all moved about and interacted with one another more than they ever had before. With such complexity in the ecology, there was suddenly a lot more to be aware of, more things that it was worth knowing about if a Cambrian animal hoped to survive. And the way to adapt to that complexity, this need for information, was to develop a nervous system that allowed a timely and coordinated response. Suddenly, it made a lot more sense to have myriad sensing organs, new forms of locomotion, and an electrochemical processor to link the two. Now it made sense to have a brain. Music. It was around this time that the first complex eye appeared in animals like the 520 million year old Aeropide Photinia. This animal had a pair of eyes on mobile stalks like in the lobopods it shared the oceans with. Scientists have found nerve tissue connecting those eyes. The addition of eyes like these, which were capable of depth perception in looking at two directions at once, contributed to the so-called Cambrian information revolution, which would have put pressure on organisms to refine their neural circuitry. When more is known about the world around you, decisions become more complicated, and it's worth investing in processing power to help make the right one. Among the remarkable radiation of new body shapes that came during the Cambrian explosion, there was one clear pattern that emerged, which can still be seen in everything from earthworms to elephants. That trend was for symmetry, and specifically bilateral symmetry, reflecting body parts down a central line rather than some formless construction of the less popular radial symmetry favored by cnidarians like jellyfish. The bilitarian body plan, as it is known, is the major innovation on the branch that leads away from sponges and corals, and in many ways enabled the ecological revolution of the Cambrian explosion. With a symmetrical body with muscles or fins or lobes or limbs reflected along a central line, moving around becomes a much simpler task. Reflecting down the middle also by extension creates a front and back, a forward and a backward, and an obvious location for sensing organs. Of course, none of this came about accidentally, but would need to be coordinated by a logical system of nerves and a processor capable of organizing inputs and outputs. It created new opportunities for action shaping nervous systems, but also required more sensory motor input than ever before. And all of this brings us to the first brain on Earth. At some point after our last common ancestor with corals, a primitive animal lived that was the first to experiment and succeed with true bilateral symmetry. No fossils have ever been confirmed, but scientists have speculatively named this missing link the common ancestor of all Belocians and Belocian because of the way this animal must have moved, sensed, and behaved. They would have been the first to require a brain. It is in this animal that we would find the most primitive brain of all. Precisely when the herbalitarian flexed its newfound brain power is still open for speculation. It could have been as early as 570 million years ago. It could be represented by or closely related to the Idiacarans Kimbrella or Sprogeno organ. It could have taken longer to assemble all the necessary parts, and the herbalitarian brain is still waiting to be found among the fragmentary fossils of the Cambrian explosion's opening act. It seems, therefore, that the prerequisites for an animal brain are somewhat unexpected. It was only once animals had developed muscles whose coordinated contraction requires a fast signaling mechanism, and when they had evolved symmetry for the coordination of those muscle contractions to make any kind of sense, that the complexity and expense of a brain became worth the effort. Once brains were part of the animal toolkit, however, no other animal hoping to compete could afford to neglect them. The larger and more complicated a body grew, and the more elaborate the behavior, the more processing power was needed. Most mollusks, including snails, clams, and limpids, live slow lives. Their fleshy bodies are protected By shells, indeed, they have been since the first shell appeared in the beginning of the Cambrian, and they move ponderously or not at all. This is not the kind of behavior that warrants investment in big brain, but cephalopods like squid, cuttlefish, and octopus with their breakaway brain success walked or floated in their own path after this group split from the other mollusks 330 million years ago in the Carboniferous. They went through their own revolution of possibility and necessity 200 million years after the evolution of Badians. The cephalopods lost their protective outer shell, making their bodies simultaneously more flexible and more vulnerable. These animals were large enough to be predators, but still small enough to be prey to bigger creatures. And this unique pressure from both sides of the ecological pyramid made it imperative that they coordinate themselves and do it fast. It's little wonder then that the infinitely flexible octopus now seems to stare back at us with a wisdom that far exceeds that of its muskin cousins. And so ultimately the evolution of the brain was an inevitable part of the rise of animals as an internal signaling and so fasting center. Its presence went hand in hand with the ecological and physiological leaps that allowed animals to break onto the world stage and makes them what they are today: larger, complex bodies and interactions needed better control, but also created more possibilities for internal feedback, at first for decision making and later for self-reflection and contemplation. That moving in the opposite direction as human brains become smaller. The adult human brain today is at least 13% smaller than that of a Homo sapien that lived 100,000 years ago. Some have suggested that this is a sign of our species' mental decline caused by changes in the way that we reproduce, caused by changes in the way that we live. Complex societies allow for the less intelligent members of a community to survive and reproduce, relying on their more intelligent peers to keep them fed and healthy, while before their lack of intellect would have been their undoing. If that is the case, we can only speculate how long this decline will continue, especially with the continuing crutch of technology to rely on. But alternatively, the shrinking of human brains may not reflect diminishing mental powers at all, but rather an ongoing structural change to our brain tissues. Indeed, we know from Phineas Gage's example that the brain is constantly changing its wiring and structure. And it may be that over successive generations, they are adapting to become more efficient, doing everything we need them to do with less physical material cost. Either way, whether we're honing or merely whittling down our mental powers, there isn't too much cause for alarm until scientists can recreate the billions of neurons and trillions of connections that are needed to build a full artificial brain and emergent sentient mind. We won't be doing without our 700 million-year-old neurological legacy anytime soon.